Hello grade 10s and welcome back to another video. In this video we're going to be taking a look at resistors in parallel. Now normally when I make the switch from resistors in series to resistors in parallel, my learners get very confused because the resistors in series make so much sense, and then we move to parallel circuits where things don't exactly behave the same and confusion reigns. So I would like to encourage each of you to grab yourself a pen and paper, take down notes as you watch this video, because the more you interact with the video, the better your chances of understanding, but also the better you're going to retain the knowledge. So you're going to remember what you have been writing down. Also, as we go along, write down the questions that you have. You can then at a later stage go to your teacher and show your teacher these questions so that your teacher can fill in any gaps that I have left out. It shows that you're taking initiative for your own knowledge, your own studies, and your own progress. So over here we have a circuit that we're going to call a parallel circuit because it contains 3 resistors that are connected in parallel. Specifically, we have resistor number 1, resistor number 2, and resistor number 3. We say that these resistors are connected in parallel simply because the current that flows through resistor 1 is not the same as the current that flows through resistor 2, which is not the same as the current that flows through resistor 3. The current through resistor 1 is being measured by ammeter 1, and its potential difference is being measured by voltmeter 1. Remember, we connect a voltmeter in parallel because it has an incredibly high resistance and no current will flow through the voltmeter. Resistor 2's current is being measured by ammeter 2, and it has a potential difference, or its potential difference is being read by V2, voltmeter 2. Lastly, we have V3, whose current is being measured by ammeter 3, and the potential difference across resistor 3 is being measured by voltmeter 3. We have over here that the resistance of R1 is 2 ohms. The resistance of R2 is 3 ohms, and the resistance of R3 is 4 ohms. So we have different resistors, or resistors of different resistances connected in the circuit. Now, connected to this parallel connection is a battery that consists of 3 cells. Together, these cells provide the circuit with a potential difference of 10 volts. And that potential difference, the total potential difference offered to the circuit, is being measured by VT, which is the voltmeter connected across the battery. In series with the battery, we have a 4 and a 5. Now, these are just ammeters, which I have numbered 4 and 5, and they are connected in series with the battery because the current that flows through the battery is exactly the same as the current that is going to flow through ammeter 4 and ammeter 5. So let's use my colorful pen in order to make better sense of this. We're going to be drawing our current in the direction of conventional current. Current is going to flow out of the positive terminal through A4 to this junction. When it gets there, the current is going to split. Some current is going to go this way through the 2 ohm resistor. Some current is going to go this way through the 3 ohm resistor, also known as resistor 2. And some of the current is going to flow this way through resistor 3, as you can see. Unfortunately, the lines are looking a bit funny, but I think you understand what I'm saying. Then what happens is all of the current comes back together at this point and will return to the other terminal of the battery, that is specifically the negative terminal of the battery, because conventional current always flows out positive to negative. What is important to see here is that the same current that flows through the battery flows through A4 and A5, but not the same current, right? So the current through A1, A2, and A3 is not the same as that current that flows through the battery or through A4 and A5. So now that you have a better understanding of why we refer to this as a parallel circuit, let's look at the relationships in a parallel circuit, starting off with the total resistance. Now we actually don't use the term total resistance when referring to the overall resistance in parallel. Instead, we use the term effective resistance. And this is mainly for mathematical reasons. Total means we're adding up. It means the sum of normally. Effective over here means the overall. And the way that we calculate or add up resistors in parallel is not the same as we do for resistors in series. We use the formula 1 over Rp, where Rp is the effective resistance of the parallel circuit, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, the way we use this formula is as follows. We're going to use the formula to determine the effective resistance for this specific parallel circuit. Always remember, you start off by writing down the formula, but I'm going to skip that step to save us time. We're going to say 1 over Rp is equal to 1 over the resistance across resistor 1 is 2 ohms. The resistance across resistor 2 is 3 ohms. The resistance across resistor 3 is 4 ohms. Okay, so those are the resistances. What we're then going to do is we're going to write down what's on the left-hand side, 1 over Rp, so that we don't forget that it's 1 over Rp on the left-hand side. And then we're going to plug what's on the right-hand side into our calculators. When we do so, we obtain 13 over 12. So you may have been tempted to convert this to a decimal, but don't do so yet. Leave it as a fraction. In order to determine Rp, which is the effective resistance, we need to find the reciprocal. So we're going to take both fractions and we're going to flip them over. We then end up with Rp over 1, which means the same as Rp, is equal to 12 over 13. Okay, so we have found the reciprocal on both sides. If we put 12 over 13 into our calculators and round it off as a decimal, we end up with 0.92 ohms. This is the effective resistance for this parallel circuit. Now, what you're going to notice is the number here is very small. 0.92 is a value that is smaller than 1. And yet, we were adding, or in a sense adding, the resistances of a 2 ohm, 3 ohm, and 4 ohm resistor. What we are finding, grade 10s, is that when we add resistors in parallel, the effective resistance is smaller than the smallest resistor. That is what we're finding. And based on that, unlike for resistors in series, when we add more resistors in parallel, we end up with a smaller effective resistance. These circuits are very different. And based on that, the more resistors we add in parallel, the higher the current is going to be that flows through the battery. Take note of that. It can be a bit confusing. But we're finding a very small number here because the more resistors we add in parallel, the smaller the effective resistance. Now we go on to potential difference. We say that in parallel, potential difference is constant. So remember, in series, current was constant, but in parallel, potential difference is constant. What that means for this circuit that we've drawn is that the potential difference that V1 measures is equal to the potential difference of V2, which is equal to the potential difference of V3. And since there are no other resistors in the circuit, specifically other resistors that are in series with the battery, we know that V1, which is equal to V2, which is equal to V3, is going to equal to the total potential difference that the battery has to offer. We can therefore say that the total potential difference that each of these devices is going to measure is 10 volts. V1 is 10 volts, V2 is 10 volts, V3 is 10 volts, and Vt, as given to us, is 10 volts. Now we go on to current. When we are looking at a parallel circuit, we say that current is divided, all right? So whereas in series, potential difference was divided, in parallel current is divided. But let's start off with the total current, and then we'll move on to the current over here, because this is where the current is divided. Okay, let's start off by finding out what the current is that flows through the battery and through the ammeters that are connected in series with the battery. To do so, we use the formula IT is equal to VT divided by RP, the parallel resistance, the effective resistance in parallel. Let's go and perform that calculation. So we have the total current in the circuit is equal to VT divided by RP, where RP is the effective resistance. This is going to equal to 10 divided by the effective resistance, which we found over here to be 0.92. When we plug this into our calculators, we end up with a value of 10.87 when we round off amperes. That means that flowing through the battery is a current of 10.87 amperes. Now, since ammeter number 4 is connected in series with the battery, and ammeter number 5 is also connected in series with the battery, it will have, or they will have, current readings that are equal to the current flowing through the battery, and they will therefore have readings of 10.87 amperes. That again is because the current flowing through them is the same as the current flowing through the battery. But over here at this point, over here, and at this point, we know that we have between these places the parallel circuit, where we have resistors connected in parallel to each other. So how are we going to find the the current that is being measured by A1, the current that is being measured by A2, and the current that is being measured by A3? Well, the formula here looks similar to that formula that we used for your series circuit, but it's very different. So please pay attention. We say that the current that ammeter A1, right? So I1, the current that ammeter 1 is measuring, is equal to the effective resistance. So the total, if we can use that word in inverted commas, parallel, or the total resistance for the circuit, divided by R1 multiplied by IT. This is a formula that will not be provided to you in your tests or exams, so make sure that you memorize it. So let's go and perform this calculation. The difference with this specific formula is that we are dividing the effective resistance by each resistor. While with a series circuit, we were dividing each resistance with the total resistance. So please be very careful. So we are now going to say I1, which is the current through resistor number 1, is equal to RP divided by the resistance of resistor number 1 multiplied by IT. We calculated IT above over here, and we know the effective resistance is 0.92. So we're going to plug the values into the formula. We have 0.92. The resistance of resistor 1 is given as 2 ohms. So we go and we plug in over here 2 ohms. And we're going to multiply this with the total current, which we found to be 10.87. When we plug this into our calculators, we obtain an answer of 5.00 amperes. That is the measurement or reading of ammeter 1. So over here we're going to write down 5 amperes. Let's go find out what the reading is on ammeter 2. To determine that, we're going to say I2 is equal to RP divided by R2 multiplied by IT. That is going to equal to 0.92 divided by 3 times 10.87. The value that we obtain is equal to 3.33 amperes. And we can go and fill that in. The reading over here on A2 is 3.33 amperes. Now let's go on to A3. So the current through A3, the current through resistor number 3 is Rp, the effective resistance, divided by the resistance of resistor 3, multiplied by the total current. That is 0,92 divided by 4 times 10,87. When we plug this into our calculators, we obtain an answer of 2,50 amperes. And of course, we can go and fill that in again over here. We have 2,5 amperes. Now, when we add up these values, we're going to see that there's actually a relationship between them. So we're going to take the 5 plus 3,33 plus 2,50, and we end up with 10,83 amperes. Although this value, this 3, is not the same as the 7, the reason is because we rounded off as we performed our calculations. But what I'm coming to, grade 10s, is that when we add up the current reading on ammeter 1, the current reading on ammeter 2, and the current reading on ammeter 3, we end up with the total current that the battery is, or that is flowing through the battery, right? So based on that, we can say over here that when we take the current through A1, A2, and A3, and we add them together, we get the total current. Now, what we will notice when we look at the current values that we obtained is that the smallest resistor, which had a resistance of 2 ohms, had a large current flowing through it. But the very big resistor had a small current flowing through it. 2,50 is smaller than 5 amperes. So what this basically means is the smaller the resistor is, right, the higher the current that flows through it is going to be. Why? It's because resistance is the opposition to the flow of charge. So therefore, if the resistance is very small, the current is going to be very high. And therefore, we expect that through resistor number 1, we're going to have the largest current reading. That is written over here. I1 is bigger than I2, which is bigger than I3. And again, the reason is because R1 is smaller than R2, which is smaller than R3. That is the reason it is so. So these relationships can be rather confusing, but with practice, you're going to make a lot of progress. So keep practicing, don't give up. Remember, you can pause, rewind, and repeat these videos until you understand. Good luck, grade 10s. In the next few videos, we're going to look at examples of where you can go and apply what you have learned about series and parallel circuits.